starting recording. Okay, so welcome everyone to the first offering of the Canadian Geotechnical Society Young Professionals Short Course. My name is Chelsea, and I'm the CGS YP Chair and Representative, as well as one of your hosts for today's session. We also have Leonardo, Nabil, and Zarin from the YP Committee joining us online. They're really the driving force behind this initiative and the incredible amount of work that went into making this possible. So a huge thank you for all your contributions to the YP community. So before we jump into the course logistics, the YP committee would like to start by recognizing a few more individuals. First, we would like to thank everyone here today who is registered and is joining in. We have participants attending from across Canada, as well as international CGS members, and we've honestly been so humbled by the level of interest and support this course has received. We'd also like to recognize our presenters who generously agreed to share their knowledge and expertise, which has been gained through years of practice. It's rare to have this level of expertise gathered in one place, and we're incredibly grateful for your willingness to share and help shape the next generation of the geotechnical community. After several months of planning, we're excited to launch what we hope will become an annual CGS YP short course. One of our main goals was to make this course accessible to young professionals across Canada, especially those balancing project work, field assignments, ongoing research, and everything else in between. This three-part short course features presenters from across North America and focuses on site investigation practices in Canada. So today marks the first session, which will feature Ken Scaffield and Dr. Peter Robertson. The next two sessions will take place on Wednesday, May 20th and Wednesday, May 27th. Throughout the course, we'll be covering a variety of site investigation techniques, standards, and testing methods, along with the Canadian-specific challenges such as permafrost and rock investigations. We'll also discuss how all of this information comes together to support practical geotechnical recommendations in both industry and academia. Each session will include two presentations, approximately 50 minutes each, followed by 10 minutes for questions and discussions. As a reminder, please feel free to put your questions in the meeting chat throughout the presentation, and we'll be addressing them during the Q&A portion. If we run short on time, we'll follow up with the presenters afterward and share response with the participants. The sessions are also being recorded, and recordings will be made available to registered participants following the course. So without further ado, it is my pleasure to introduce our first speaker for today, Ken Scaffield. Ken Scaffield will be presenting on geotechnical site investigation techniques and standards. In this presentation, Ken will be sharing valuable insights on the site investigation methods described in the 5th edition of the CFEM, with reference to key technical standards, as well as regional and international standards. Ken Scaffield is a senior geotechnical engineer with Trek Engineering, with 42 years of consulting experience in site investigations, foundation design, cold region engineering, slope stabilization, and rehabilitation of aging infrastructure. Ken graduated in 1979 from Red River Community College as a civil technician, and from the University of Manitoba in 1984 with his bachelor's in civil engineering. He completed a Master of Science in Geotechnical Engineering at the University of Manitoba in 2014. Ken was also the co-editor for the 5th edition of the CFEM. What Ken doesn't mention in his bio is the incredible amount of mentorship he has provided to engineers throughout his career, both in the private and public sectors. I'm personally very fortunate to work alongside him at Trek and can easily attribute so much of my professional and personal growth to him. Okay, Ken, I'm gonna pass this on to you and we'll get things kicked off.
Thank you very much, Chelsea, for that kind intro, and thanks to the rest of the YP committee for putting this on, and certainly thanks to all the attendees today. I'm just going to share my screen. Chelsea, you see that okay?
I do. You're all set.
Okay, perfect. Okay, here we go. Geotechnical site investigation techniques and standards. I'm not going to talk a lot about standards. Don't necessarily have a a standard per se or a code that we follow in Canada, but we'll touch on some of the other codes that are applicable in terms of setting up a site investigation. One important tool in your toolkit for a site investigation is a thermos with coffee, and then you always need an office chair. This is a picture taken somewhere in the high Arctic several years ago. The picture on the left is a sonic drill at a project up in the Yukon. And now my dad joke. I'll give you a chance to read that. And I promise that's the last dad joke. There are no more. So what is a site investigation? Really, it's an assessment of the physical, like the engineering properties, the physical properties of a soil, rock, and let's not forget groundwater, because that's a super important part of a site investigation and design and construction for sure. So this is at a proposed construction site, or it could be a site where problems have impacted constructed works. An example of this would be we have a diversion channel runs from the Assiniboine River to Lake Manitoba, and there was a lot of flood damage to some of the bridges. So this is an investigation that is being carried out. This happens to be a track-mounted auger rig. And then why we did the work was to look at conditions relative to, in a number of cases, relative to exposing the footing or the pile cap, I should say. You can see the steel H piles below the pile cap. We extended the pile cap down and with concrete and then armored it. And in some cases, there were additional piles added to some of these bridges and so on. So this is an example of a problem that has impacted constructed works. So the general purpose really is to obtain data, geotechnical data or groundwater data on soil and rock strength, compressibility, permeability. Those are maybe some of the more important ones, but there's others. We want to identify, the presence of potential hazards such as landslides, expansive soils, etc. This is not a site investigation, but it's a picture of an unexploded ordnance and somebody sneaking up on this person in this picture. Sorry, that's my dad joke number 2. So that is definitely going to be it. The primary purpose is to systematically assess, and systematically is an important term. You'll see further on, like we want to get as much of a systematic process as possible. So that's to assess subsurface condition and guide us as to how we expect the ground to respond. And that would be the response under loading. Don't forget about unloading. Rebound is something to think about in that particular case. Environmental effects, there's numerous environmental effects that could include wetting, drying, especially in like our region and where Chelsea is in Saskatchewan, we have expansive clays. Then we also deal with freeze thaw in this part of the prairies. So really, what I just described above requires an understanding of subsurface investigation techniques and principles. You should be familiar for sure with design procedures, applicable codes, construction methods, and at least a working knowledge of geology and hydrogeology. Those are all really important. And these are things that you're going to gain along the way. But the more you understand these and appreciate some of these, especially things like codes and construction methods, the easier it's going to be to plan a site investigation around what's being built or designed. So there's 2 approaches for a site investigation. I mean, basic approaches to collect data for design. This is a reference I've just shown here, geotechnical investigation handbook, and it's also got a lot of design tables in it. So I'll leave that for you. Some may have this on their shelf. The traditional approach to geotechnical site investigation is to consider ground conditions as a design element based on a structure or a development design, or maybe layout that's been given to you. So somebody says, this is what I want to build, and then you're going to plan your approach based on what's being built. That's probably the more common approach. Having said that, and I'm not sure I like non-traditional, but it probably is in some respects, where we might want to plan the structure and development around the ground conditions. And so the ground conditions would be a design input. And so the design is based on those conditions, and that's maybe less common. There's 3 basic steps involved in a site investigation, and there's obviously more steps, but this is what I consider perhaps to be the basic steps. You've got to determine the level of information required. In other words, what does this investigation look like? Is it a desktop study? Are you doing preliminary design? Is somebody doing preliminary design, say on a bridge, or is it detailed design, and so on? And that will really determine the level of investigation that's required. The second step is to determine, and this sometimes isn't all that easy, but you got to determine the extent of the investigation. For instance, the number of boreholes, the depth of those boreholes. It doesn't necessarily have to be boreholes. It could be test excavations, test pits, and so on. And then you have to carry out that investigation. So now you've determined the level, you've determined the extent. Now it's time to execute. So you have to carry out the investigation. This is where it's really important. Once you've gone through steps 1 and 2, then you should have some idea of what the right equipment is. Like if you got a wet sand, you're drilling through 40 feet of wet sand, you're probably not going to have an auger rig, and so on. So you want to make sure you have the right equipment and also the right personnel. So a fundamental question or a fundamental consideration is what are the geotechnical design issues and what are the questions? So ask yourself, what are the loads? Not unusual for us to ask a structural engineer if they're looking for a geotechnical investigation for a building or a bridge. We'd like to know what those, ballpark, what are the loads on the foundations. We need to have some understanding, obviously, of ultimate limit state and SLS values. Long span length equals large loads. So quite often there's a lot of discussion relative to shorter spans, longer spans, and the impact that will have on foundation loading. And therefore, that sometimes drives the type of investigation that's needed. Do we need to get into bedrock and this sort of thing? Are there slope stability concerns? I would think in this picture, the answer is pretty obvious. Are retaining walls needed? Quite often there's geometric constraints that prevent the use of, just earth embankments with, 4 or 5 to 1 side slopes. This is an MSC wall in Saskatoon. Will fill be placed for an approach embankment? So if fill is being placed, what are the sediment tolerances? And so the reason I'm showing you this is so you start thinking, well, okay, if there's really strict settlement tolerances, you better get your investigation better look at, the type of soils, the compressibility of the soils, and so on, and plan your lab testing program around that. Is there pile down drag? In a lot of cases, when there's an embankment and it's a short time frame to construction, quite often there's down drag loads on the piles that has to be accounted for. There may be frost heave, and don't forget groundwater. That's my main take-home message for today. Don't forget groundwater. So what's the importance, in my mind, of a good site investigation? Almost everything, like all foundation elements and a lot of utilities, most utilities, lie in or on the ground. So we need to find something out about the ground. Quite often, geological, geotechnical, hydrogeological conditions are often poorly known. We may not really have any information to go on. Sometimes we have some information. A very important step in all this is to obtain as much information ahead of time as you can when you're planning a site investigation. Unknown or poorly known subsurface conditions represent the largest technical, and I can assure you, if it becomes a technical risk, there's probably a financial risk associated with that relative to claims and so forth. So that's what we deal with. An inadequate subsurface investigation is quite often the cause of a large claim or a large delay. If there's a large delay associated, say, with changed ground conditions, I can almost assure you it'll be followed by a rather large claim. So what are the realities we work with? We deal with complex geological conditions that are hard to understand sometimes, difficult, challenging to model. There's quite often a complex response to loading or unloading, and that generally will depend on the stress level. In other words, how deep. We quite often have stress strain behavior that might not be linear. And for instance, in a normally consolidated clay that I'm showing here versus an over consolidated clay. So these are the challenges that we're faced with. And then we need to look at the stress range that we're working with, the loads and so on. Probably one of the first things to look at really closely is the classification of soil and rock. That's a really fundamental objective of a site investigation, is you got to classify the soil and rock. So to do this, you need to have a good understanding of soil and rock. And the Canadian Foundation Engineering Manual, the 5th edition, has adopted entirely the Unified Soil Classification System, or USCS, as outlined in the following 2 standards. CFPM is not a code. It's a guideline document, but the USCS follows standards. The first one being ASTM D2487, and that's the standard practice for classification using USCS, and 2488 is the visual manual method. Now, I'm sure most of you are aware of this, but just as a reminder. So why would we classify soil and rock? To consistently identify them in a particular group. And we can all basically understand the same language if we do that. We want to specify a particular soil for an engineering application. Maybe you have maybe you've got a liner and you need a highly plastic clay, so it's a CH, a well-graded gravel, GW for road, and so on. And I'll be given a plug for the CFEM from time to time, just to refer you to Chapter 4, Classification in Soil and Rock, and the 2 lead authors on that. The 2 authors were Leifa Cow from WSP and Jennifer Day from Queens. Just to clarify one thing on USCS, that is the system. ASTM is the standard method to execute it. So that's got the standards are part of ASTM. And D2487 is the one standardized procedure, which includes mechanical and sieve analysis, and this gives us consistent testing to classify based on grain size and plasticity. 2488 relies on, this is the visual manual method. This relies on manual tests in the field. This is more for the field, right? So this is part of your site investigation. And we record those classifications on field logs, and that's a preliminary assessment. Quite often that's followed up by lab testing in accordance with the ASTM. So a site investigation should consider the testing requirements needed to properly classify the soil. And that's changed a little bit over the years, but you should be aware of what sampling is needed and what testing is needed when you're laying out the program and identifying the laboratory testing program. I'm not going to spend a lot of time talking about rocks other than to say you've got somewhere along the line, if you're dealing with bedrock, rock needs to be classified. This is pretty basic stuff. We've got igneous rock we've got sedimentary rock, and we've got metamorphic rock. If you're, some people, I'm sure, attending today have a geological background. So I'm just going to tell you if I have my toolbox and I need to look at some rock more closely, chances are I'm going to bring some back for a more complete classification. But you'd want to have a rock hammer, you want to break off a piece of rock, a pocket knife to scratch the surface. This goes to the Mohs hardness scale, a hand lens to look at the crystal, just to see whether it's coarse or fine grained, a dropper bottle with diluted hydrochloric acid to test for carbonates, and a paintbrush. It's always good to wet the rock sample if you want to have a better look at it. Objective 2, determine the physical properties. So this will help assess the suitability of the soil or rock for construction. This is how I kind of like to look at soil. We have index properties, which are specific gravity, water content, or moisture content. Same thing, particle size, density, plasticity. Then we have engineering properties, permeability, shear strength, and compressibility. Those, in my mind, are the engineering properties. By the way, this slide is from probably around 1914, construction of the Shoal Lake Aqueduct. At that time, this is someone classifying the soil in the excavation. The instructions to the inspector was to look for soil that was poorer than best, but better than worst. And that was all they had to go on. We've come a long way. Rock mostly just has a bunch of engineering properties, and you're going to hear more about this in another presentation, so I don't want to spend a lot of time, but weathering and joint discontinuities and so on. So once you have a feel for the variability of the soil, then the results of the laboratory testing, modeling, and design values should become clear to you. Objective 3, assess bearing capacity. Evaluate the maximum load to a soil that a soil or a rock can safely support. And that would be what we refer to as the ultimate limit state. And also without excessive deformation, and informing about the type of and size of foundation units, which is the serviceability limit state. So I don't want to get bogged down in limit states design here, but just a few things. When we look at a footing, obviously as the footing width increases, the behavior in both SLS and ULS limit states changes, right? And so quite often, we look at different footing widths and so on, and we try and find a balance between strength and serviceability as much as possible. Sometimes we start with a footing size that's based on serviceability, especially in a really soft soil or a loose soil, because generally speaking, once serviceability criteria have been met, then ULS requirements are probably satisfied. Objective 4, geological hazards. There's that same unstable slope, liquefaction potential, obviously, during seismic events, expansive soil, and this is a fairly common problem in the prairies where we have lacustrine clays. Liquefaction potential is certainly a phenomenon in Eastern Canada with Leda clays and Lake Champlain clays. Frost susceptibility, anything that could potentially impact the project's stability, basically. Objective 5 would be locate groundwater levels. This is of critical importance in order that you can get the information that you need to look at dewatering strategies. And that might be like here's showing a short excavation sheet pile. Top right picture is a sheet pile supported excavation. There's a pump, there's dewatering going on, and so on. Sometimes dewatering wells are installed outside of the excavation to lower the groundwater levels and so on. This is a picture from one of the floodway bridges built back in the 1960s, just outside or just east of the city here in Winnipeg. And Frank Render, who was our groundwater guru for many, many years, Frank passed away. But this shows an excavation for a pile cap, steel H piles. This is not like surface water going into the excavation. This is groundwater that's coming up around the piles. There was very little clay left. The piles went down into till, which is common here, and all kinds of groundwater seepage into the excavation. So this is another excavation on the south end of town, just showing what the rock looks like, the jointing and so on. This is a limestone bedrock, and these are some of the challenges that we're faced with. So it's also really important identifying groundwater levels for foundation design, assessing buoyancy potential groundwater contamination. So it is, and by it I mean groundwater, is sure to play a very important role. Just want to give you an example. This is downtown Winnipeg, right here. You can see this is the groundwater level in 2008. You can see that it's depressed in the downtown area by like, more than 10 meters. And that's from all the historical pumping that went on. Since then, groundwater levels have started to rise because net consumption is way down from what it was. So now we see that groundwater levels are now, this is the 2008 level. Sorry, I made a misreference the first line here, but this shows the current level. So there's about a 7.5 meter rise from where it was to where it is now. What does that mean? There's where it was, let's say back in the 70s, you put a deep excavation in a basement, underground parking, whatever. That's where your groundwater level potentially would be if it broke through into the excavation. Fast forward, 20, 30 years, the groundwater level is now here. And now the potential groundwater level and seepage into a structure, a basement, let's say, could reach this elevation. If you look at that in terms of, this is work by Sarah Kloss in 2010, these are groundwater contours, red being a higher elevation, blue being the drawdown cone right here. That's shown in the blue here. If you look at it in time lapse, you'll see that the dates, sorry, it's a little bit faster than I like, but anyway, you can see that blue area just basically disappearing. So you can see kind of the two-dimensional effects. Objective 6, to guide foundation design. So identify the information necessary to select a cost-effective foundation type. And you want to provide data for the design of the foundation system based on the anticipated loads. And that could be a shallow foundation, deep foundation, raft, and so on. Many different types of foundations. We generally classify foundations in terms of either being shallow or deep, but in both cases, they transfer load down onto the soil. Shallow foundations, there's general kind of rules of thumb in terms of what defines a shallow foundation based on the depth and the width. And these are some different types of shallow foundations. Whereas a deep foundation, it's when the depth of the foundation is really large in comparison to the width. Think of it that way. And that could include belt piles, cast in place, concrete piles, driven steel pipe piles in the bottom right. Could have a mat or a raft foundation. This is an example, classic example. I'm sure you've seen this either in a presentation I've done or in textbooks. This is the Transcona grain elevator, which failed. There's a bearing capacity failure, but it's a really good example of a mat foundation. There's a number of columns that transfer the load down to a mat, or in this case, actually 2 mats. And the bearing capacity was exceeded, and this is a classic failure. Could be an excavation, it could be a secant or a tangent pile wall, which are very similar. The tangent pile wall, the individual piles are just touch each other, where the secant pile wall, they bite into each other. So in terms of a site investigation for something like this, you better have test holes deep enough to reach refusal or to reach a sufficient depth for the design of this. You need to know something about the undrained shear strength of the clay for design, unit weight, groundwater level, friction angle if it's granular, modulus values, and so on. For an MSE wall, where we have steel strips going back to hold up the, basically so we can achieve pretty much a vertical face with face panels that you see here. The use may be limited by the bearing capacity of the foundation soil. This is a pretty big load and it's not over a sloped face, so you better have holes that are deep enough, and you probably want samples for odometer testing to look at settlement magnitudes. You probably need effective stress parameters for analysis for global stability, unit weight, and so on. I kind of like this because this is how I always remember. The stressed area is larger underneath a load here on a, let's say it's footing, but it's larger than the dimension of the loaded area, which is B, by an amount approximately equal to the depth. So this is B plus Z. So it's kind of a handy thing to remember if you're trying to look at the distribution of stresses with depth through a soil layer. Seventh objective, optimize construction methods. So we need that to look for different excavation types and techniques. You need earth pressure coefficients for retaining structures. You need to determine safe excavation side slopes and so on. So you need to also look at ground improvement needs. There may be ground improvement techniques that could come into play. So your site investigation needs to carefully consider these things relative to what data do you need to collect in order for somebody to design some of this. This is just a typical soldier pile shoring system in Winnipeg. This is a deep excavation into shale, and you can see the the amount of bracing and whatnot that is required. So it's a pretty big difference between the two. Nonetheless, you need to obtain the information necessary for, in most cases, the structural engineer to design the system. Need to ensure regulatory compliance. That would be, you might have to provide some documentation for local, provincial, and federal building codes. You may need to demonstrate, that might be an assurance letter or something like that. You need to demonstrate that the project design recommendations are based on sound principles and meet safety standards, say in this case, as an example for seismic design. And so we deal with the National Building Code of Canada, NBCC, and I think everybody would be familiar with it. We also deal with the Canadian Highway Bridge Design Code, CHBDC. There are some differences, and I don't want to get bogged down. I think this is coming up in another presentation, so I'm just safe to say that NBCC does not prescribe geotechnical resistance factors in the code itself. So that's left up to determination by a suitably qualified engineer. Recommended values are provided in commentary K, which is kind of a commentary that's linked to the code. And CHBDC gives us the ability to pick a resistance factor based on our understanding of conditions. And this is a really important point because the resistance factor accounts for uncertainty, and it depends on the degree of site prediction and model understanding. So this ties right into, well, if you consider you want to look for a high degree of understanding and take advantage of a higher resistance factor, then you better make sure you have the right information. Your site investigation is tailored around that. So it's a real economic value in many cases to have a resistance factor that can be adjusted. And sometimes on a job where you got many piles, then it may be worth going the extra step, getting that level of understanding that a good site investigation will provide. That could mean static load testing, or it could mean Osterberg load testing or something like that. So just high understanding, this goes back to CHBDC, high understanding, that might mean CPT testing, a typical understanding, and I'm just kind of throwing this out there as an example, kind of in my mind, what the level of investigation might include. And then a low understanding, that might be you've got a site a block away and you're taking some information from that site. So this kind of scales up or down according to your level of understanding, and the resistance factor is tied to this. So what do you need to know to plan and implement this site investigation? Is it conceptual, feasibility, preliminary, detailed, design? Sometimes there's a bit of an overlap between these. They're not necessarily in a box to themselves. And sometimes we carry out a detailed investigation, a level of investigation that would be sufficient for detailed design as part of preliminary design, because it's maybe not cost effective to go back in for a second round. Maybe it's a very, very remote site and expensive to mobilize and so on. So sometimes these overlap. You got to ask yourself again, loads and allowable differential settlements. It's not just settlement. So when you're looking at odometer results and you're looking at consolidation settlement, it goes way beyond just the settlement magnitude. You really need to consider what the differential settlement is potentially going to be, what information is available for the site, and how many boreholes do you need, and where will those boreholes be located, within or outside of the footprint. Sometimes there's a building on the site and you can't get to where you might want to get to, so you have to plan around what's there. There's physical restraints. What are the sampling requirements, disturbed and undisturbed? Think of undisturbed, and I would put relatively undisturbed samples, that being, say, Shelby tube samples. Should in situ tests be done? Dr. Robertson in the next presentation will be going into a lot more depth on in situ testing. Is instrumentation needed, and what does that look like? Do you hook it up to a data logger? You just go out and do manual readings? How do you protect that during construction? Maybe it's really important to maintain the instrumentation like an inclinometer casing during construction, then you better put it somewhere where it's not going to get taken out during construction. So your site investigation should plan around what's being built, and if you've got instrumentation, try and put them in the area and a location that's least likely to be damaged or disturbed. So there's a lot of stuff to think about, right? I put this together, and I'm sure if you threw this out there to 10 different geotechnical engineers, you might get, like, how we seem to all kind of gravitate towards flowcharts. This is my own flowchart, starting with a preliminary investigation and what that might mean relative to getting to preliminary design. And after preliminary design, do you have sufficient information? Yes or no? If you don't, then you might have to go back around and drill more holes, more test pits, and so on. So it's just a kind of a way to logically think your way through this, right? So we'll go back up to the top. So your preliminary investigation, you're going to collect some initial information. You'll have a site reconnaissance and public records maybe, and you're going to characterize that, and then you're going to get into the preliminary design, which involves drilling and so on. Along the way, there'll be some technical review, and that's probably going to direct you on one path or the other. So I don't want to get too bogged down in this, other than to say, give some thought as to what the typical, or what the investigation should look like relative to the project that you're working on, and whether it's preliminary, detailed, or conceptual. I think this shows up. This is Dr. Robertson's. It's a really good illustration of a site investigation that's based on risk. And risk is an important thing for us to think about and be aware of. Low risk, moderate risk, and high risk. This is probably going to be covered, I'm sure I saw it in one of the other presentations, so I don't want to spend a lot of time other than you should be aware of that. It's also in Chapter 5, Site Investigations, and the Foundation Manual, and the author is Dr. Dave Elwood. This, I'm not saying you could find this, because I might have the only copy. It's a short course on site characterization that was put on by Wayne Clifton and Dr. Robertson back in can't make that out, 19 something. So it's a great publication that was that put together lots of interesting papers, lots of good resource material. So if you can get your hands on a copy, I'd suggest you do so. Geotechnical data and baseline reports. I want to touch on this quickly. A GDR is a data report. There's a GDR, D as in David, and a GBR, B as in Bob, and the GDR represents a general description of conditions and information collected. That's all it is. But more importantly, a geotechnical baseline report, you're going to be hearing about these. You're probably going to run into them. You're probably going to be involved in one. The intent of a GBR, especially for linear infrastructure like tunnels, that's where this comes into play a lot, would establish baselines that you can measure that describe the ground conditions and behavior that you expect to be encountered. A classic example is obstructions in tunneling, and they're called obstructions. You think of cobbles, boulders, that sort of thing. So the GBR is really essential for allocating risk and developing scope, and as part of contract administration. If you think of the opportunity when you have feasibility, then you're into detailed design, construction, and operation of whatever it happens to be, the opportunity to minimize risk is really high in the feasibility stage. As you get into construction, it becomes more difficult, and operation even more so. The cost of changes looks a little different. The cost of a change is probably low during feasibility, but I can tell you that a change after you're in operation can be very, very expensive. So the GBR provides a contractual mechanism to evaluate those. So this, I can tell you from experience that the level of site investigation that may be needed to prepare a geotechnical baseline report is considerable. And the more information you collect, the better that you can kind of define or describe those ground conditions and determine what values you might expect. In other words, on a percentage basis or whatever the case may be. That information is then given to the contractor for the purposes of bidding. If there's more, if something that you quantify turns out to be a lot more, i.e. boulders, then that's the basis for payment to the contractor. There's a picture from a tunneling job showing what we don't like what tunnel boring machines don't like to run into. There is a document by ASCE on geotechnical baseline reports you might want to be aware of. And that describes basically what I just had there. Expenditure for a site investigation. The typical expenditure may range, and I'm just throwing some numbers out. Again, it's like that flow chart. You ask 10 people, you're going to get 10 different numbers. Let's just say, for argument's sake, 0.1 to 1% of the construction cost. And it may be more for if it's complex, and the minimum may be something like 0.2 to 0.5. Some may say the cost of an investigation has increased over the years as awards may be based on lowest cost and fastest results. That's the reality of the world we live in. An interesting paper by Littlejohn shows different consumers and what they thought the cost of a site investigation was relative to what it actually cost as a percentage of capital expenditure. So I'm not picking on anybody, but if you let's just say architects, for instance, thought that this site investigation was maybe 0.29, whereas the actual expenditure was 0.14. So it's interesting. Civil engineers may look at it a little differently. They would have expected the thought that cost should be 1.94%, whereas it turned out to be 0.29. So it's an interesting thing to look at relative to expectations, I guess. But what does it really do to help identify what a site investigation is worth? And I dug this up because this shows you the total increase in construction percentage. This is kind of like what we showed in the previous slide as a percentage of tendered price or capital expenditure, basically, versus the site investigation cost divided by the capital expenditure. So you can quickly see the relationship, I guess, between what you're spending and potentially what the benefit is. So without getting too bogged down, it's just an interesting observation in terms of what people's expectations are, because the reality is you're going to be providing clients with proposals for site investigations, and sometimes the reaction is, well, why is it costing so much? And so you can at least, maybe walk an owner through some of the risks associated with what could be an insufficient site investigation or not. A site investigation plan, number and spacing of boreholes really depends on the project size and risk. Spacing should be sufficient to adequately identify major soil units. I'm just going to show you 2 boreholes, and I'm going to show you the difference between two boreholes. These are soil layers. You've got 5 soil layers. 1 hole drilled here, you identify 3 soil layers. 1 hole drilled here, you pick up all 5 layers. This is a snip from a presentation Ralph Peck did in Winnipeg on site characterization, and the title was Expect the Unexpected. So just keep this in mind, especially if you've got complex geology. Chelsea, how am I doing for time?
You're doing good. You're at 40 minutes.
40 minutes, so at top of the hour?
You got it.
Okay, I should be good. Another example, so planning a site investigation, we quite often look at LiDAR. It's such a valuable, LiDAR is like between LiDAR and drone surveys, and they go hand in hand now. This is a river, this is the Red River in Winnipeg. This is the North Kildonan Bridge. And you can see, based on elevation, brown being higher elevation, green being lower, you can see that this ground is higher by a couple of meters. That's because this is lacustrine. This is the original lake bed, Lake Agassiz clay. There's been a lot of erosion going on, and on the inside bend, that's where the deposition is taking place. That's why the elevation is lower, because of it's a floodplain, and the soil ground elevation really only gets to kind of where the water gets to, because it's a depositional material. But you can expect entirely different conditions between borehole 1 and borehole 2. Look at this and anticipate what you might need for drilling. Hollow stem augers probably for borehole 2, maybe solid stem augers and some coring for borehole 1. If you look at, say, a cross section, here's the lacustrine clay. This is on the inside bend where alluvium has been deposited. We call this an erosion controlled bank. Here it's failure controlled because the lacustrine soils are weaker and they tend to fail, deep-seated failures. We have till with some boulders, and we have limestone bedrock. Maybe you have a high rise here and a building here. So start thinking about that site investigation. What do you need to find out? Well, on this particular side of the river, it's probably below flood protection level. So you're going to need maybe a dike. That dike, you're going to have to start looking at stability of this alluvium. So you need information on that. You'll need information on this, on the shear strength properties of the lacustrine clay for sure. And you got a high-rise building. So this borehole probably goes down into rock to get enough information for deep foundations. These loads can be substantial, and quite often we use rock-socketed caissons. So you need information on the bedrock. Your investigation needs to go down into bedrock. And because we no longer go down and inspect those holes, then our site investigation has to obtain enough information beyond the length of socket that we anticipate. And then we can look at what socket length is needed based on what we find in the coring. Whereas we used to go down and core the bottom of the caissons to make sure we had good rock for some distance below. This test hole here, smaller building, maybe the important thing becomes seepage and whatnot. Maybe that's something that, permeability testing or a test like that to look at potential seepage paths underneath the dike and so on. So depth of exploration depends on ground conditions, depth of bedrock, what's being built. If you look at stress bulbs, that's a good way to kind of figure out how deep you need to drill based on Boussinesq stress bulbs. Lightly loaded structure, 2 to 6 times the probable footing width, and so on. So there's some general guidelines you can use. Keep in mind that 10% or the 20% isobar, which is 10% basically of the loading, like this is the stresses being distributed, obviously. So outside the stress bulb, we consider it to be the stress change to be negligible in terms of relative to settlement. 10% is quite often a standard boundary, whereas Tersaghi recommended 20%, which is great. But if you only think of it as 10% and there's a soft layer down below, you've got to start thinking about, maybe you need to take this hole a little bit deeper, because there could still be, depending on the difference between 0.1 and 10% and 20%, you could still be stressing that soft soil, and that could result in more settlement than you expect. So the client may dictate site investigation requirements, so you should keep your program flexible. Existing site development may limit the extent of the exploration. Here's a small compact electric drill and inside a building. So equipment availability often controls the type of exploration. You could have remote communities with difficult access and so on. Looking at the cost of a geotech, this is a similar graph. You've probably seen enough of this now in terms of the cost of the investigation relative to, think of it as total project costs. So I'm just going to really fly through this, just looking at different drilling and sampling methods. Mud and air rotary, good for all soil and rock types. Sampling is a bit of a problem. You can go deep with this type of drill. It's portable. You can take it in with a helicopter, and so on. So this is one type of drill rig available that will go through just about anything. This is more conventional, where we have a solid stem auger rig. It's pretty cost effective compared to some of the other ones. I don't think we need to explain to everybody what a solid stem auger looks like, but it's good for cohesive soils and non-cohesive soils as long as they're above the water table. So finding out where that water table is important. Practical depth, 100 feet. That's kind of my rule of thumb. And you can get relatively undisturbed Shelby tube samples as long as the hole stays open. Then we have hollow stem augers. Same rig, it's just you're switching over to a hollow stem auger. So the auger becomes the casing, and you drop down your sampling devices inside the hollow stem augers. It gets really expensive beyond 50 feet. Hollow stem drilling becomes it's exponentially more expensive the deeper you go. But it's a great choice for soils that both below and above the water table. The sonic drill, it just basically, just based on the name, it's got a sonic percussion system. It's efficient. It's suitable for most soil and rock types. You can get continuous core samples, large diameter casing, and so on. Nice that you can CPT cone penetrometer capability. So this is more and more common now. A lot of the this is maple leaf drilling in Manitoba here, the sonic drill. Percussion hammer drill, like a Becker hammer, not all that common for site investigations, but it'll go through some, say, waste rock in a mine, something like that. Sampling is so-so. Don't forget the hand auger. It is useful sometimes. You can go 10 or 20 feet if you're ambitious enough. Different bit types and so on. Power auger. This is something you want to be very careful of. If that auger bites in the ground, you'll be spinning around like a top. In situ testing, Peter's going to talk on this shortly, so I don't want to take any time. Evaluate soil in their natural and undisturbed state. In situ testing, that's the beauty of it. It'll largely, not completely eliminate sample disturbance, particularly in cohesionless soil. Good for looking at layers that might be missed if you're sampling every 5 feet and so on. Geophysical methods, I am going to just really go through this quickly, and I apologize just to make you aware that there are geophysical tools and methods out there that can greatly help in a site investigation compared to, say, a one-dimensional information provided by a CPT, let's say, in this case, whereas you get more of a two-dimensional picture from geophysical. And there's a number of different methods out there. The results are qualitative, limited applicability for deriving geotechnical parameters directly, and so on. So I'm just going to show you this, that here's a drill holes, and if you are doing conventional drilling, you might find the clay over limestone, but you'll miss the void, the boulders, the limestone pinnacle, the spaceship, and the skeleton. So it's really good to work along with an intrusive investigation. It's a very, very good companion investigation. You still need drilling. You still need to drill holes as a minimum to calibrate the geophysical model. So there's seismic surveys, there's electrical resistivity. Chelsea, I don't know if anybody's covering geophysics or not, but just so you know what's out there, ground penetrating radar, I'm sure everybody's heard of. Quite often used nowadays to look at permafrost table, depth of thaw. This is an example of some work I was involved in looking at deteriorated concrete in a concrete pipe. And we use something called impulse radar scans to identify sections of pipe with sulfate attack. The last few comments on site characterization. Here's this famous picture from Ralph Peck's. This is myself with Michael Bozizek, and here, that's me, younger me, Michael Bozizek and Ralph Peck, who are both passed away now, and Dr. Jim Graham. And we awarded Ralph Peck with this dancing bear, which I carried around for about a month up north from site to site. We bought it, can't remember exactly where, somewhere in the Eastern Arctic. Anyway, he had an absolutely amazing presentation on site characterization. Super interesting projects he was involved in, most notably the Chicago Tunnel. Just the last comment here is, this is the level of detail. They sampled like every few centimeters. We're taking moisture content so they could draw moisture content contours in a very, very small area, a 1 foot square, and then develop these relationships, knowing that there's a relationship between moisture content and initial voids ratio. Peck developed a relationship, therefore, between, because this is relatively easy to do, and he developed this relationship between initial voids ratio and compression index, just to give you an example of how important and how detailed sometimes these investigations should be. Do not underestimate the value of moisture content. So I was told that when I first started, and I began to appreciate it more throughout my career. The moisture content profile can tell you an awful lot about what's going on in the soil. Whoa, look at this. Time to pack it in.
Oh, you have to fit one more joke in, hey?
I did, yeah. Sorry, I rushed through the geophysical stuff a bit. I'm not 100% sure if that's going to be covered, but I think it's important to know that that is something that you should be aware of, and I'm sure lots of people sitting in on this are familiar with those techniques and the advantages and disadvantages of anything. Like I said it, I'll say it again, that joining those to a good ground investigation with boreholes along with the geophysical exploration can be a very, very valuable combination. So.
Yeah, 100%. That was a very thorough, almost masterclass of an introduction. So thank you. I'm just seeing that there's some comments in the chat, but it's many thanks and compliments on your presentation. I do have a couple questions myself. It's very
Uh-oh.
me. And I think it's, yeah, just from my own experiences and something great to talk about. Maybe not a straight answer, but so say you have local information, you know, it's a project site or area you've worked on before. How local is local enough to be optimizing your drilling program? And is that more of a risk-based thing? You know, what cost is available? Yeah, I'll let you answer that.
We generally only, like, if you're drilling like on a site, it's pretty dangerous to proceed based on just local information alone. I'll give you an example. The precast concrete pile study that was done many years ago determined that we probably had a 30%, we probably could increase our, and this going back to working stress, our 50, 70, 90 tons for precast piles in Winnipeg. They felt that that could be bumped by 30%. Now that's huge, and I only know one engineer that recommended 30% higher capacities because that was based on a small site with good till. And so if you are sure that you've got a small site with good till, maybe that's something you want to take into consideration. But it becomes typically you want to use whatever local information is available to plan out your investigation and logically, right? And determine what, especially for a site investigation, what are you expecting to encounter? I'm not saying that that would be a rationale, unless it's a purely conceptual level design where, okay, we want to build a dike here, and you say, well, based on the regional geology, it's full of alluvial deposits, silt and sand. So here's what the problems are going to be. Fair game. But when it comes to building that dike, you better have more specific information.
Awesome, great answer. Uh, so more compliments again to your presentation. Do you have another, unless someone has a question beforehand? On remote sites, I'm sure people eventually learn it. It's important to expect the unexpected. Do you have any pro tips to share on planning for things like site access, what tools you should be bringing with you, the driller? This is a very broad question, but I'm sure you've probably learned either through being very prepared or being very prepared quickly.
Well, you know, that depends on where the site is. And I can tell you from experience, we mobilized to a site by aircraft, spent days getting into the site, had everything ready for site investigation, mini excavator, ATVs, everything. And two things happened. The shifter pedal on the ATV broke like the first 5 minutes. So we replaced it with a pair of vice grips. So have some, like, be prepared to MacGyver. But the other thing that happened was we were missing a cable for the total station. And okay, so go get a cable. Well, that's a big deal, right? As you could be days away from getting that cable. So I think not that you're going to bring anything and everything with you. I have my typical toolbox of, I don't get out in the field as much as I'd like to anymore, but I had a toolbox full of stuff that the regular pocket pen, Torvane and whatnot, but other things that might come in handy. As far as the drillers go, the expectation is that they're going to have everything they need. I think everybody in this room that's been involved with field work will know that every once in a while, what do you mean you need more than 40 feet of augers? Well, so it's hard to say, but it's kind of like make a list and check it twice, and bring along more than you expect to need. It's tough for drilling because if you don't know whether you need solid or hollow stem augers, chances are you're going to bring both, right? And that becomes a big factor in mobilization. So you want to try and nail down as many uncertainties as you can. Depth is quite often an uncertainty. So you want to make sure you've got extra drill rod, extra augers. If all of a sudden, instead of a 60-foot hole becomes a 100-foot hole, it's a lot easier to have that equipment with you. And you have enough Shelby tubes to go beyond what you think you might have to go to. You have enough sample bags and so on. So
Awesome, thanks. We had a couple questions pop into the chat. I think we have just enough time. The one from Piash would be, what would be the mitigation measures for a site with high lacustrine clays?
With, sorry, hi.
Probably highly plastic lacustrine clay is what I'm thinking here. And maybe they're referring to the construction mitigation measures, but Piash, if you want to provide a bit of context on that.
I'm not so highly plastic clay in terms of mitigation measures that let's look at, say, an excavation. Um, stability is a big concern, obviously, in an open cut. And we get involved quite often in designing anything in Manitoba that's more than 3 meters has to be engineered, have an engineered design. And we quite often then look at alternatives to an open cut. We look at, soldier piles and lagging and so on. So I'm not sure if that's what the mitigation measures this person is referring to or not, or whether I answered the question, but
Yeah, I think you're covering it there, even the consideration of like basal heave and all that.
oh yeah, basal heave is a big one, and I'll give a 30-second thing on basal heave. That's huge because if that basal heave, don't confuse that with basal instability, which is like a slip surface that develops along the outside of the shoring and pops up. Basal heave is when you put, say, a shoring down on, say, a rectangular shoring down, and there's only 3 meters of clay or 4 meters of clay left, but you've got a till or a sand or a gravel layer that's under, got a piezometric level that's much higher than the base of the excavation. The CFEM does a very good job now in terms of how do you analyze that relative, because the clay will do this. It'll bulge up if there's not enough weight. If the self weight of the clay is insufficient, it'll bulge up. It'll start to crack. The minute it cracks, water comes in. Then you've got a huge problem to deal with. CFEM now has, or Foundation Manual has ways of looking at it in the traditional approach, which is just the ratio of weight of clay to the pore water pressure, right? The head, essentially. Now they have instructions on, or guidance in how to look at that more from a limit states perspective. So that's a big concern relative to deep excavations in lacustrine soils that are underlain by till, which is hydraulically connected to the limestone bedrock quite often.
Awesome, thanks, Ken. We're getting close to the end of the Q&A. We are planning just to have a 5-minute break at the end of this, but I think if people want to drop off starting just at 10 after to do that, I do know you're a great storyteller, so I think it would be a nice way to conclude this by answering the question that says, how was your experience doing site investigations in the Arctic?
Yeah, that's a good question. My professional experiences were phenomenal. I was the site investigation task leader for a lot of the work that I did when I was formerly with UMA Engineering, became AECOM. So I spent many years in the Arctic. Site investigation techniques in those conditions are very different, very unique. And the logistical side of those investigations was as big as anything else, because you had to plan flights, planes, equipment, weights, everything. Stovetop espresso maker had to arrive. There's no doubt about that. So professionally, it was phenomenal. The reality is, on a personal side, you're away from home, right? And that's the reality. So the one take home would be, if you're in sort of have the same opportunity, you want to make sure that you have support at home that allows you to to go away for extended periods. Things are a bit different now because communication is so much better, right? But I tell you, and I'd love to do. Did Brent do a talk on site investigations in the Arctic?
You did. You guys can catch that on our YouTube page.
Okay, so
Yeah.
yeah, yeah. So anybody that I worked with in the north in the Arctic had a passion for it, and it's a fantastic way to see parts of the country that you're very likely not going to see. You know, you go say, well, I'm going to go fishing, 100 miles outside of Cambridge Bay. Well, you better pony up $10,000 for a charter. So, I mean, we were, literally we were paid to go and visit these places and do some really, really interesting work. It was probably, I think the work I did on the Shoal Lake Aqueduct and the rehabilitation of the aqueduct and the work I did on the Dew Line are, two projects that I, think back on as, they're all important, but they were, I think, some of the more memorable projects.
Awesome. Well, thank you, Ken. You have so much more to share, I know. But we just want to give you a virtual round of applause and just thank you for all your contributions to geotechnique and to the YP community.
Well, thank you very much. Thanks for listening to my dad jokes, and look forward to Peter's presentation. So,
Awesome. Thanks, Ken. And thanks, everyone. So we're just going to take a quick break. Maybe you want to run and have a bio break, whatever the case may be. We'll return here at 20 after, and then we'll get things started with Dr. Peter Robertson. Thank you, everyone, and thank you, Ken.
Hi, can you hear me?
Hey, we can hear you,
That's good.
and your presentation looks great.
I don't get to see what I look like on the camera. Is the camera centered? I can't see.
There you go. Yeah, we can see you at the top, and others might have different presentation modes, but yeah, we can see you. We're just giving a couple more minutes for people to
Sure.
join us
Yep.
again, and then
Yep.
Leonardo will kick things off. Okay, it looks like we're all set to resume. Peter, we lost your camera, but I think we'll get that back shortly. Perfect. Okay, I'll mute myself.
Okay, you want me to start? Okay, well,
Uh,
yeah, are you going to
uh,
introduce me?
yeah, I was
Okay,
just
go ahead.
about to. Welcome back, everyone. I hope you have a chance to take a break and grab some coffee. So, as Chelsea mentioned earlier, my name is Leonardo. I'm with the YP community, and we're very excited to be launching this. Particularly excited to introduce this speaker because for many of us, when I was in the undergrad, and I'm pretty sure for everyone else, there was one specific document that was always open on the desktop, the guide to cone penetration testing. So it was really an important instrument for my own learning and understanding the raw data, how it integrates. And that's what we're going to dive into the presentation today. So Dr. Robert Peterson will be presenting on in situ testing and soil behavior classification. He has more than 50 years of experience as an educator, researcher, consultant, and practitioner specializing in the areas of in situ testing, site investigation, and soil liquefaction. He's the co-author of the primary reference book of cone penetration testing, as well as the free CPT guide. Peter has also assisted in the development of several inexpensive CPT-based interpolation software programs and has presented a series of free webinars in an effort to enhance education and practice. Peter continues to provide private consulting to a wide range of clients and currently resides in Southern California. Beyond his impressive technical accomplishments and international recognition in the fields of in situ testing and soil liquefaction, Dr. Robertson has demonstrated an incredible commitment to advancing site investigation practices and mentoring the next generation of geotechnical professionals. Through more than 100 short courses and 249 publications delivered around the world, he has made geotechnical knowledge and CPT education available to practitioners and young professionals across the globe. Dr. Robertson, it's such a pleasure to have you join us today. The floor is yours.
Thank you for that kind introduction. It's nice to be with you, particularly for a group of young professionals. So I'm going to focus on institute testing and soil behavior classification. And I got into focusing a lot on site investigation and eventually institute testing because in my work experience as a young engineer, both in the UK, in Canada, and in Hong Kong, I very rapidly realized that site investigation was the key to a lot of our engineering. Without a site investigation, you can't do pretty well anything else in geotechnical engineering. And so I very quickly realized that this was an area I wanted to understand more. And in doing so, very quickly realizes that traditional ways of drilling and sampling and lab testing had a lot of challenges related. And so I ended up focusing on in situ testing. So let's get this going. And so when it comes to in situ testing, why is it of interest? And so if you look at the advantages, one is you test a large volume of soil. So typically when you drill and take samples, the samples are usually relatively small. And by the time you get it into a lab and do some testing on it, say like a triac or consolidation, the sample is very small. Whereas with in situ testing, you'll see that a lot of them end up testing quite a large volume of soil. And something like the cone penetration test, which is continuously measuring while you're pushing in. So you end up testing a volume of soil that's maybe 10 diameters of the size of the probe, and the probe is 37 millimeters in diameter. So sort of almost half a meter in diameter of the volume of soil you're testing, and you test it continuously. So if you push 20 meters, that's a lot of soil you're testing. And because the test is fast, you can do repeated tests around the site. So you end up testing a large volume of soil. And then, of course, you also test it in its natural layering, fabric, and spatial variability. You're not losing any of that. You can also test difficult to sample soil. So I got into in situ testing because I realized that we were relatively good at taking pretty good quality samples in clay and doing lab testing, but of course we were not very good at testing sands. And so my graduate work was really in situ testing and its application to liquefaction, and that's because liquefaction is one of the biggest issues for sand. And so you can test loose saturated sands where it's very difficult to get samples in that material. And you also test them in their natural environment with their in situ stresses and layering, etc., and any fabric that they've got, and if they're lightly cemented, etc. You get to test it in the natural environment. And also reduce cost and time. Often in situ testing, as we'll see later, CBT is fast and cost effective. Now, the limitations is that it's complex and poorly controlled boundary conditions. So when you're doing a lab testing, you can close the drainage valve and run the test undrained, or you can open it and run the test slowly to ensure it's drained. But with in situ tests, if you're carrying it out at the standard rate, and we do that to standardize the procedure and the data, then it's not always fully drained, and it's not always fully undrained. And so sometimes you can get partial drainage occurring. And so the next one, uncontrolled drainage conditions. And then the soil disturbance. Obviously, most in situ tests involve some disturbance. So penetration tests, you're pushing some probe into the ground or hammering it in the case of an SBT. And so there's large soil disturbance. But we get around that by the fact that you're doing it in a very consistent repeatable manner. And so when you push the cone in, obviously you're disturbing, you're failing the soil, but the point is you are failing it, and so you are getting measures of the strength of the soil. So the disturbance is not that big of an issue because it is being influenced by the undisturbed soil around the probe. And of course, most in situ tests have non-uniform strain fields. In the lab, we try to have relatively uniform strain fields. We don't do it exactly very well, but in the field we have much more complex non-uniform strain fields, and also the deformation and failure mode from the in situ test may be different than your design problem. So you may have a slope stability problem, and you need a certain type of strength, whereas the strength you're measuring from an in situ test may not exactly be the same. So you have to compensate for that. And then also limited identification of soil types. So a lot of in situ tests like the CPT, where you push it in, you don't get a soil sample, so you don't get to see it. But we'll talk about how you can overcome those problems. And I want to reiterate something that was touched on a lot by Ken, which is really the importance of geology. Now, I've had the privilege of working in many different places around the world. I was born in the UK, worked in the UK, moved to Canada, worked in Western Canada. I lived and worked in Hong Kong for a while, and later in life have been involved in projects all over the world. And when you travel and you work in projects all over the world, you begin to realize the importance of geology. You need to understand what the local geology is, and therefore how your site investigation is going to be impacted by that geology. And we're going to talk a lot about in situ testing. So we're focusing on softer ground, and often because that's where geotechnical challenges often are, sand, silts, and clays. But in some regions, where bedrock is close to the ground surface, or in Canada where you've got glaciation, where you've got dense glacial tills, it's important to understand the type of geology and how that impacts the site investigation. But for here, we're just going to focus on softer ground. And many years ago, actually, the first version of this table was produced by Jim Mitchell, probably about 40 years ago. It's gone through various iterations. And what it is, it's a table that tries to show the applicability of in situ tests. So on the left-hand side, it lists most of the major in situ tests, from penetration tests, pressure meters, and other types of tests. And then in the middle are the soil parameters, from soil profile, strength, stiffness, compressibility, stress history, etc. And then in the far right, it says ground type, from hard rock all the way down to very soft organic soils. And A means highly applicable, B means moderate applicability, C is low applicability, and if there's a space, it's not applicable. And so we're going to be focusing on these penetration tests. So the CPT with pore pressure measurements now, which is pretty standard, the seismic CPT, and I'm going to touch briefly on the flat plate dilatometer and the standard penetration test. And one of the reasons we do that is that the CPT is one of the most highly rated. There's a lot of A's and B's across there. Now, of course, when you get to ground type, you can see it's generally limited to sand, silts, and clays and organics, and a little bit in soft rock. I live in Southern California. The geology here is mostly soft rock. And so we push CPTs into soft rock quite regularly here. Obviously, you cannot push it into hard rock, and you have challenges in gravel. If it's a gravelly sand, you can push it in, but if it's predominantly coarse grain gravel with cobbles, you're not going to be able to push it in. So it does have a limit in its range. So let's quickly go through the major tests. So standard penetration test, been around a long time, over 100 years. The advantage is it's very simple, rugged equipment, relatively low cost, available throughout, it says the US, available throughout North America, and of course it's available in most parts of the world. And you do get a soil sample. The sample is disturbed, but you do get to see what the soil looks like. The limitations are that the sample is disturbed, so it's only for index testing only. High variability and uncertainty. And the variability comes from exactly how did you make the borehole? Where's the water in the borehole? What type of hammer anvil system did you use? So the biggest one is the variability in energy from the hammer anvil system. And it's a pretty crude number. You just get a single value, the blow count, to penetrate the sampler a foot. And of course, it's discontinuous. Typically, you run the test every 5 feet or 1.5 meters. And so if you do a 30-meter sounding, you only get about 10 blow counts. And when you're going to process the data, it's common now that you normalize it to an overburden pressure of 1 atmosphere. That's the N1. and it's common practice to try and correct it to a 60% energy. And that 60% energy comes from the fact that a lot of the historical data and the historical empirical correlations were based on data where the average energy was typically around 60%. Nowadays, with modern automatic hammers, often the average energy is up around 80%. So generally, you're measuring lower blow counts than historically, and so you need to correct it to that energy. So here's the corrections, and so you've got the energy, the overburden correction, and then there's a slight correction for rod length, especially for very short rods, borehole diameter, and sampler correction. Not all samplers are exactly the same. So they can have a liner or not a liner, etc. So there are these corrections. And in simple terms, so you may measure a blow count of 12, but if you were using a very old system like a rope and cathead system that could have an energy of only 40%, then the N60 gets corrected down to 8. Now, if you've got a modern safety hammer with automatic safety hammer, then it could be operating up around 80%, which means the N60 is 16. Now, of course, at shallow depth, the energy can be even lower. So for a rope and cathead type system at shallow depth, it could be as low as 20%. So it could be as low as 4. So the real blow count is somewhere between 4 and 16, and you measured 12. So you're not actually quite sure exactly what this blow count is, unless you measure the energy or you have a calibrated system where you have some sense of what the average energy is. But even if you have some sense of the average energy, it will vary a lot, and so there's a lot of uncertainty. I'm just going to touch briefly on the flat plate dilatometer. It is a relatively popular test. It was developed by Professor Silvano Marchetti in Italy. When I lived in Italy for a year and a half, Silvano and I became very good friends. And the advantage, it was a very simple and rugged piece of equipment. It's a flat blade. You can see a picture on the side. So it's a flat plate, and it's got a circular membrane. It's a stainless steel membrane. And there's a little air tube that goes down, and you inflate this membrane. So you take two measurements. One is the lift-off pressure to just get it to lift off, and then the second is the pressure for the middle of the membrane to have moved 1.1 millimeters. And then in recent years, Silvano's son, Diego, has taken over. Sadly, Silvano passed away a few years ago, but Diego now runs the business, and he has an electrical engineering background, and he added seismic measurements. So he added geophones to it and sort of increased the level of accuracy of the device, and she can now measure shear wave velocity. Typically, the test, you run the test every 20 centimeters, so 8 inches. And so you don't get as much detail as the CPT. You'll see later the CPT typically collects data every 1 or 2 centimeters. So the CPT will collect 10 times as much data, and you'll get a more detailed profile. So the flat plate dilatometer doesn't collect as much data, and it is a slower test because you push it, you have to stop, inflate the membrane, deflate it, and then push to the next depth. So it's about 3 to 4 times slower than the CPT. And it's a little bit bigger than the CPT, so it's actually harder to push into the ground. So if you have a given reaction, so a given piece of equipment, then you're not going to push this as deep as the CPT. And of course, you don't get a sample, and penetration is restricted in gravels and cemented layers and rock, etc. And also, it gives you a lot of parameters, but it will not give you residual strength. So if you want the residual remolded strength of a soil, this is not going to give it to you. So this is what it looks like. You get these two readings, P0 and P1, and then you get these 3 parameters, the material index, which is basically the difference between the 2 readings normalized by the liftoff. And then the horizontal stress index is the liftoff pressure minus the water pressure divided by the vertical effective stress. So it's a bit like K0, but it's KD because it's influenced by the fact that you push the blade in. And then they give this third parameter, which is dilatometer modulus, which is sort of a very simplistic, elastic calculation. But ED is actually a function of the other 2 measurements. So ED is actually this constant number times ID and KD and vertical effective stress. So the third parameter is a combination of the other 2 parameters. And then Marchetti developed this sort of soil classification system based on the ID value. And this ID, remember, is essentially the difference between the two measurements normalized by the liftoff. And so if the difference between the two is very small, you're into clays. If the difference is very large, you're in sands. And he set levels of 0.6 for clays and 1.8 for sand. And if it's between those two values, you're in silts. And this is the sort of data you get nowadays. So this is the seismic flat plate dilatometer. And so you get a soil profile, and they've color coded it as we've progressed. And so you can see here they've got blue for clay and sort of greens and yellows for sands. And so you get one-dimensional constrained modulus, the peak undrained strength, and friction angle in sands. And you can see there's only a little bit of sand here, so just a couple of dots for these two sand layers. And then you get this, the KD is the index, which is sort of linked to OCR. And then also he's got seismic. So what he did is he developed a module that went behind the blade, and the module is a little over 0.5 meter long. It's got two geophones 0.5 meter apart, and so if you hit a beam at the surface, the shear wave travels down, and you get the arrival at these two geophones, and you calculate the velocity you get. So you get this velocity profile. So the DMT takes measurements every 20 centimeters, and you measure shear wave velocity every 50 centimeters, every 0.5 meter. So now if we look at the cone penetration test, so the advantage is fast and continuous. So it's pushed in at 2 centimeters a second. So that's basically 1 meter a minute. So you can do a 30-meter sounding in about an hour. It takes about 30 minutes to go down and 30 minutes to come out and get ready to move on to the next site. So you can do a 30-meter sounding in an hour. So in a day, you could do 200 meters depending on how far apart the holes are, etc. So you can get a lot of data in a day. It's repeatable and reliable, just like the DMT is. Oops, sorry. So repeatable and reliable data. It's economical and productive. So because of the rate, it makes it economic. In the early days, people often thought that things like CPT were expensive, and that's often because they were mistakenly looking at the day rate. They would say, well, the day rate for the CPT is more than the day rate for a borehole. And it says, yes, but the CPT is going to collect you 5 times more data, or you do 5 times as many locations as you can with a borehole. And so, of course, it makes it overall much more economical and productive. Strong theoretical basis. CPT's been around for 50 years or more. So there's a lot of research done on it. Early on, it was mostly experimental, and then it's moved more into the theoretical basis. So lots of theoretical work. In the early days, very basic theory, bearing capacity, then cavity expansion. Nowadays, with numerical modeling, has become quite advanced and sophisticated. The key thing is you've got multiple measurements. So a standard cone would be tip and sleeve. I'll show you that in a second. And then pore pressure. And then if you stop and do a dissipation test, so if you're pushing into a fine-grained soil and you develop excess pore pressure, you can stop and then allow that excess pore pressure to dissipate. And if you measure the time to 50% dissipation, you get T50, and then eventually you get equilibrium pore pressure. And with geophones added, you can also get shear wave velocity, and more recent years, P wave velocity. So you get a lot of measurements in one test. The limitations, somewhat high capital costs, little obviously more expensive than the SPT, a little bit more expensive than the DMT. Somewhat skilled operators. In the early days, that was very true because they had to know how to interact with a computer data acquisition system. But nowadays, most people, of course, are comfortable around computers, so that's less so. You don't get a soil sample, just like with the DMT. At least you don't get it while you're pushing the CPD, but you'll see that you can, in fact, use the pushing equipment to push in samplers and get soil samplers with samples. And of course, you've got restricted penetration in gravels and cemented layers, just like the other penetration tests do. So the common misperception is often people think that the problem with the CPT is you don't get a soil sample. And that's true. While you're doing the CPT, you don't get a soil sample. But in the early days of the development of the CPT, particularly in Holland, where it first originated, they have soft soils there. And so they very quickly developed push-in samplers that often looked exactly like the CPT, just that they had no electronics or load cells in, as is illustrated on the picture on the right here. And you would push it to a depth, and it's like a closed-ended, small diameter fixed piston sampler. And so you would retract to expose the sampler, and then it would lock into place, and you push to get a sample, and then extract the whole thing to get your sample. And so often people think, well, this must be quite slow because you're pushing the cone in at 2 centimeters a second. But when you're taking samples, you can push in as fast as the equipment can go. And with modern CPT trucks, you can push in 10 to 20 times faster. So you can actually get samples pretty quickly. And so the common practice and the preferred practice is that you push the CPT at a given location. And then once you've got the profile, you then move over about 1 meter and you go down with these push-in samplers. And you take a small number of selected samples. So you look at the profile that you've got from the CPT, and depending on the geology and the type of project, in other words, which of the layers that are going to be most important to you, and then you move over and then you push down the sampler and you take selective samples in the layers that are going to be of most importance for the project. So instead of the traditional approach where you maybe send a drill rig out and you do SBT with samples every 1.5 meters, and so for a 30-meter sounding, you maybe come back with about, I got this number right, maybe 10, 15 samples. With the CPT, you've got a continuous profile. It's collecting data every 2 centimeters, and you've got 3 channels of data: tip, sleeve, and pore pressure. And then you take selective samples. So instead of coming back with, say, from a project where you might have 100 samples, of which none of them are actually in the important layers, just because you took them at regular depth intervals. Whereas here, you'll come back with samples, every one of them in the layer that's most important for that project. So that's important to remember. When it comes to pushing equipment, there's a huge range of equipment. Here in Southern California, these big trucks are popular, and that's because Southern California is an urbanized area. So there's a lot of people here, and so these big trucks become very effective. So they typically weigh about 25 tons, and the pushing equipment is at the center of gravity. So you can push with 25 tons very quickly. These are very, very efficient systems in an urbanized area. But you can do CPT with various pieces of equipment. Down in the bottom right hand, here's a very sort of simple system put onto a front-end loader. And here you can see they're hitting the beam to do seismic. And in the bottom left-hand corner, you can see this is actually a small auger rig modified to push CPT at the back. So these are just an example, but there's actually lots of different examples around the world. And in many places now, when you get out of the urban areas, you're often seeing small drill rigs that have been modified to push CPT, so that you've got the ability to both push CPT and to drill and take samples together. And Ken touched on the issue with the growing popularity of sonic drilling. I don't have a slide here, but one of the manufacturers of sonic equipment developed a little hydraulic ram set that would fit in the jaws of the sonic rig. And so before you did the sonic drilling, as long as the geology was suitable, then you would put the CPT ram set into the jaws of the sonic rig, and you would do static CPT from that location. And then when you'd finish that, you move the hydraulic ram set out of the way, and then you could do sonic drilling right over the same hole that you just put the CPT. So you get a continuous core of the material that you just pushed the CPT in. And so sonic is now becoming a very popular way of doing that combination of CPT plus drilling and sampling. Often the question that people ask is, how deep can I push the CPT? And that's true for how deep can I push the flat plate dilatometer as well. And of course, it says, well, depends on the reaction force you have. So, and also it depends on how hard the ground is and the amount of rod friction. Because if you just take a steel rod and you push it into the ground, very quickly you accumulate a lot of friction on the side of the rod, and you will meet refusal because of the growth of rod friction. So standard practice in the CPT world is that when you're pushing a cone in the early days, the cone was 10 square centimeters in cross-sectional area, which meant it was about 37 millimeters in diameter, is that about a half a meter back from the cone, there would be a bump in the rod. And the bump in the rod was to push the soil away from the push rods so that you would reduce the amount of rod friction. And so that bump in the rod was referred to as a friction reducer. But here in North America, 15 square centimeter cones have become very popular. They're 44 millimeters in diameter, and they're also accepted in the standard. ASTM standard accept both 10 and 15 square centimeter cones. And the advantage of the 15 square centimeter cone is that it's already larger than the 10 square centimeter push rods. So you don't need a friction reducer. So it actually takes less push force to push in a 15 square centimeter cone than it does a 10 square centimeter, because you have less rod friction, because there's less distance between when you drop to the small diameter rod. And so this is a plot of push force, either in kilonewtons or tons, against like a blow count N60. And you can see that if you have 20 tons of push force, you can push into ground that's equivalent to over 100 blow count. Now, given that the SPT begins to level out at 50, so it's a nonlinear relationship. So anything past 50 blow counts starts to become meaningless. But here it's assuming that it would be continued to be linear. And you can see you can push into very dense ground. So you can push into very hard ground. So with these trucks, you can pull up to a parking lot with a blacktop and just punch it straight through the blacktop. Typically, you don't do that because you might be concerned of what utilities is underneath that roadway. So typically, you make sure that there are no utilities, and it's common to hand auger the first few feet to make sure you're not going to hit any utilities. But you can push through very hard ground. And so here in California, it's very common to push into soft rock. These are siltstones and clay stones and weak sandstones. And the CPT has been pushed almost 200 meters, 170 meters is, to my knowledge, the deepest CPT in relatively soft ground conditions. That's a long way down. That's longer than, that's deeper than quite a few of the drilling methods that Ken mentioned. Ken mentioned like 100 feet for hollow stem auger. So that'd be about 30 meters. So you can see you push the CPT a long way, providing you have adequate reaction force. So typically 15 to 20 tons is preferred. And of course, a 25-ton truck gives you that immediately. But if you have smaller, lightweight equipment, that usually means you've got to anchor it down. And so those pictures of the equipment, those smaller, lightweight pieces of equipment, they all had anchoring facilities where you could increase the reaction force by anchoring it down. So what does the CPT measure? So it obviously measures the depth, keeps track of it while you're pushing it in. And it's got two load cells inside. One load cell that measures the force on the tip. And when you take that load and divide by the cross-sectional area, you get the tip resistance, referred to as QC. And then there's a second load cell, and that's attached to the sleeve. And so it measures the force of the soil as it passes the sleeve. And so the sleeve friction, or the sleeve resistance, is that load of the soil passing the sleeve divided by the surface area. So it's in units of stress. So you've got tip and sleeve in units of stress. And then usually there's a porous filter element. And the most common location is just behind the tip. In the early days, it was on the tip, but it suffered a lot of damage, and now it's become popular to put it just behind the tip, and that's referred to as the U2 location, U1 being on the face. And so you measure pore pressure in units of stress. You've got tip, sleeve, and pore pressure all in units of stress. And also, you measure the rate of penetration, since you're measuring depth, and the computer acquisition system tracks time. So you track the rate, and the standard rate is 2 centimeters per second. And then most cones have simple inclinometers. In the early days, just a very basic inclinometer. Nowadays, pretty sophisticated inclinometer in both X and Y direction. So you can keep track if the cone is not going in vertical. And also most cones now have temperature sensors, and that's used primarily to make a temperature correction to the load cell. So if the load cell heats up too much, or if it cools down, like in Canada, if it's a hot sunny day and then you push, and then when you hit the groundwater will be quite cold. And so there's a temperature shift, and most cones have a little temperature sensor to correct for that temperature effect. So you got these are the measurements. They're not always presented, but they're gathered, and quite often the contractor can present that information if needed. Additional measurements, I mentioned about seismic, shear wave velocity, and P wave velocity. There's also modules to measure electrical resistance, sometimes referred to as resistivity. There's passive gamma, so just to measure the gamma, natural gamma background of the soils. There's also vision cones. They haven't become too popular, but a little camera on the side of the cone where you can actually look at the soil. Of course, when you're passing through granular material, it's quite insightful. But as soon as you pass through clays, it's rather a little boring to watch this fine-grained material go by. But there are certain applications that it's found some uses. Not that common, but there are applications. And there are lots of other modules, particularly in the environmental world. Ultraviolet induced fluorescence and membrane interface probe, and then more recently nuclear magnetic resonance, sometimes referred to as just magnetic resonance, to get water content. So Paul Main put this nice little figure together, and he was saying the conventional approach was that you drill holes, and of course you could drill a hole, measure the SPT blow count in the sand, and if you went down into the clay, you might have a vein shear test that would measure the peak and remolded strength, so you could get undrained strength and sensitivity. And if you had particularly harder ground, then you would could do a pressure meter test. Now, if it's soft ground, you could do a south-bore pressure meter, but that's quite complicated and difficult to do. And then in stiffer ground, there's pre-bore pressure meter tests, which can give you modulus of the ground. And then, of course, you can do seismic as well, either cross-hole or down-hole, to get shear wave velocity and P wave velocity. And sort of the modern technology is what Professor Main says, direct push technology, where you can push the cone in, you get tip, sleeve, pore pressure, dissipation, and seismic. And it's fast, continuous, repeatable, and cost-effective. So you can see that this is the trend towards the future. And so what you're tending to see is Ken lives in a geologic environment where he quite often referred to the need to do boreholes and sampling and test pits, etc. But if you're in soft ground conditions, often a preferred approach is you push the CPT first, because your geologic model says we are anticipating soft ground conditions. So I'm anticipating that the CPT is suitable here. So I'm going to push the CPT first, and that's going to give me excellent stratigraphic background. Well, if I go back a step, if it's a high-risk project, I'm going to do geophysics first. And so things like MASW, which is surface seismics, which gives a two-dimensional shear wave velocity profile. So I get a two-dimensional profile of shear wave velocity, so I can identify where the soft and stiff ground is and match that to my geologic model. And then based on that, I do CPTs, I get continuous profiles, and I can do dissipation tests, get groundwater conditions, etc. And then if it's a high enough risk project, I would then follow that up with the boreholes. So do a small number of selective boreholes in locations where the ground conditions are most critical for the project, and then focus on getting high quality samples for future laboratory testing. That tends to be where the industry is going. So when it comes to CPT interpretation, here's sort of a visual. So I've got these measurements from the cone, and I can get soil profile, which is usually the first thing, and that's what we're going to talk about mostly today. But I can estimate the state of the soil, either in terms of relative density or state parameter for sand or for OCR in terms of clays. And then I can get the strength and stiffness, so I can get the peak drain friction angle or the undrained strength for clays and remolded undrained strength. And I can get the modulus from shear wave velocity. So I've essentially got the stress strain curve And if it's a clay, I can get stress history, compressibility, and when I do dissipation tests, so I've got a dissipation test, and the time for 50% dissipation is a measure of the rate of dissipation, which I can then use to get the coefficient of consolidation and permeability. So I can get virtually everything I need from this in situ test. And then for high-risk projects, it's nice if you can then take selective, high-quality undisturbed samples, do the relevant lab testing, and then compare the lab samples with the CPT to check if the interpretation is valid and whether or not any adjustments need to be made for your particular geology. So when it comes to classification systems, the traditional one, and Ken touched on it, is based on physical characteristics. So here in North America, the Unified Soil Classification System is the most popular, but all the systems around the world are very similar. For coarse-grained soils, it's based on a grain size distribution, and for fine-grained soil, it's based on plasticity. So coarse-grained soils is, more than 50% passing the number 200 sieve or greater than 75 microns. And fine-grained soils is less than 50% retained on the 200 sieve. And then you look at how plastic it is high or low plastic, etc. And then what it doesn't say here, of course, is ideally you also want in situ water content. As Ken said, when you're in fine-grained soils, the in situ water content is a very important measure. So in the CPT world, you could estimate the unit weights and water content. I won't go into that in detail, but ideally you want to take samples. So if you move over and take samples, then these small disturbed samples, if it's in fine-grained soils, you want to take in situ moisture contents and Atterberg limits. And so ideally, if you've got a deep fine-grained clay layer, then you want to do that as frequently as possible to get a sense of how the water content varies with depth and how the Atterberg limits vary with depth. So that's really useful. But the key to remember is all of these tests are done on remolded samples. So it's a rather weak link to the in situ behavior. So certainly if you know what the water content is relative to the Atterberg limit, you've got some idea of what the in situ behavior is. So for example, if the water content is close to or higher than the liquid limit, then you know that the material could be sensitive and when it's remolded would have quite a weak strength. So a rule of thumb that's useful to remember is the undrained strength, the remolded undrained strength at the liquid limit is approximately 2 kPa. It's a very small number. So if the in situ water content is equal to the liquid limit, then you would expect that the remolded strength would be in the order of about 2 kPa, which means that if the sample is coming from any reasonable depth, it's likely to be very sensitive. And if the water content is higher than the liquid limit, it's likely to be more sensitive. Now, if the water content is close to the plastic limit, it's likely to be a stiffer, over-consolidated soil and much stronger. And so Atterberg limits and moisture contents are valuable to get. But when it comes to in situ testing, they don't measure grain size distribution and plasticity directly. So the CPT, for example, is based on the strength, stiffness, and compressibility. So when you push the CPT in, you're having to fail the soil to push the probe in. So obviously it's a direct measurement of the strength of the soil. And of course, the stiffness of the soil plays a role as well. The stiffer the soil is, then the higher the cone resistance is. And then it's also influenced by compressibility. So in organics, it's very compressible. And of course, some sands can be very compressible. So the Dutch, when they first developed the CPT, and they realized they could identify the type of soil, and they realized that you could identify it primarily based on the cone resistance and the slope of the sleeve friction to the cone resistance. So they developed this parameter friction ratio. And that's basically the sleeve resistance divided by the tip resistance in percent. So it's the relative friction, how much the sleeve friction is relative to the tip. And in the early 80s, this sort of chart became very popular, which is tip resistance on a log scale from 1 to 1,000 atmospheres, and then friction ratio also on a log scale from a very small number of 0.1% out to about 10%. And most data fits within this region. Very, very rarely does it fall outside of this region. And so we identify sort of 9 zones. And so clays tended to fit in the bottom right-hand corner, so they tend to have low tip resistance and high friction ratio, and sands tend to have higher tip resistance and lower friction ratio. And when color printers came along, we color coded the chart, and so we gave sort of these brown and orange colors for the sand, and blue for clay, Boston blue clay, and green for silts. And then the red, so if you've got a sensitive clay, it plots in the lower left-hand corner, which means the sleeve friction is lower than you would expect for a regular clay. And that's because the sleeve friction is essentially a measure of the molded strength. And so the more sensitive it is, the lower the sleeve friction is. So the friction ratio gets smaller, even though the tip resistance is very low, typical of a soft clay. So this is color-coded red as a warning, could be sensitive. And then way up in the right-hand corner is where the sort of cemented and soft rocks, so they're color-coded gray. So most normally consolidated soils plot down the middle of the chart. So, roughly that diagonal middle version is where most of the soils plot. So this basic chart, which was over 40 years ago, was based on data that was generally collected from a depth less than about 20 meters and on average 10 or 50 meters. So basically, roughly at an overburden pressure of an effective overburden pressure of about 1 atmosphere. So these charts work pretty well as long as you don't push the probe too deep. So as long as the CBT is not going too deep, these charts work really well. What you find is, let's for example, if you're in a normally consolidated clay, at shallow depth, yep, the data will plot exactly where a normally consolidated clay should plot. Relatively low tip resistance with a friction ratio of 4, 5, 6% in this region. But if it's normally consolidated, then the deeper you go, the larger the undrained strength is. The undrained strength ratio is roughly constant. So the deeper you go, the bigger the undrained strength gets. And so the higher the tip resistance gets. So the deeper you go, the data will keep migrating upwards in the chart. And eventually, if you go deep enough, you start to get the classification incorrect. So that led to normalizing the data. So the basic data, here it is, just an example. So tip, sleeve, and pore pressure. And I'm showing this as an illustration to show how much variation there can be. High tip resistance in sands, low tip resistance in clays. And then if you look at the pore pressure, it's showing the hydrostatic line. And so in clean sands, there are no excess pore pressure. So the penetration pore pressure is roughly equal to the equilibrium one. Here it's hydrostatic. And then when you enter soft clays, you typically get these larger positive excess pore pressures. But in denser sort of silty sands, you can get negative pore pressures, or at least negative of hydrostatic. So the pore pressure can go plus or minus depending on if it's contractive or dilative at large strains. And then here's the full set of data. Now, the one little difference is, notice it says QT here. So the measurement is QC, which is the load divided by the cross-sectional area. But in the early days, we recognized that when you lowered the cone in water, particularly for offshore work, that it didn't always measure the correct water pressure on the tip. And that's because the O-ring seals are inside by the sleeve friction. And so water gets in behind the shoulder of the cone. So the net area of the cone, when there's water, is smaller than the gross area. And so there's a small correction for that unequal end area effect for the water. It's a very small correction. In sands, the correction is essentially zero because sands have a high tip resistance and very little excess water, and so the correction is insignificant. But in soft clays, the correction can be a little bit more important, but in general, no more than about 10%. So it's a very small correction to correct to QT. Most data acquisition systems do it automatically now when you've got pore pressure measurements. So QT is done automatically. And you notice too here that what's happened is someone at Conetech came up with a great idea that since we had color-coded the chart, is you could take the color from the soil behavior type chart and you could put it underneath the tip resistance. And so you would see the tip resistance, and the color would automatically give you a sense of what the soil type is. So you can see the brown layers with the high tip resistance of sand, and the weaker layers are sort of silty clays. And so you visually see that quite well. And so I forgot to mention that, because the CPT responds to the behavioral characteristics, that's why we refer to the classification as a soil behavior type classification, not to be confused with the traditional classification from the unified classification system. So in the early 1980s, Professor Roth gave his ranking lecture, and he said that ideally we should be normalizing the data for vertical effective stress. So he suggested that we should use a normalized cone resistance, which is the net cone resistance divided by the vertical effective stress, and then the normalized friction ratio is the sleeve resistance divided by the net cone resistance. It's a small detail, but certainly normalizing with effective stress is important. And then there were also these normalizations for pore pressure. BQ became the most common. This is the excess pore pressure, so the measured pore pressure minus the equilibrium divided by the net cone resistance. And then in 2009, I sort of said, well, Roth was correct, but when it comes to sands, this linear normalization isn't quite right. So that made it a little bit more complicated. So it's the net cone resistance divided by atmospheric pressure, so it becomes dimensionless, and then atmospheric pressure divided by vertical effective stress to the power n. And in clays, n is 1, and so it goes back to what Roth had suggested based on clays. But in sands, n could be less than 1. And so for very dense sands, it could be as low as 0.4, and then eventually would move up to 1 in looser sands and at high confining pressure. So I came up with a way of how you would estimate n, and it's based on the soil type. So it's an iterative process, but it only takes a couple of iterations to get it to home in. And so everything we're going to see now is going to be this normalized cone resistance, normalized with a stress exponent of n. And so in 2009, I sort of updated the charts. Actually, I updated them in 1990, but then again in 2009. So here's the 2009 version. So you've got normalized cone resistance on a vertical scale, again over 3 orders of magnitude, and then normalized friction ratio. And of course, sands tend to fit in the upper left corner, clays in the lower right-hand corner. And so in sands, the penetration is predominantly drained, and in clays, the penetration is predominantly undrained. And the soils in the middle, the mixed soils like the silty sands, silty clays, that's where partial drainage can occur. And Mike Jeffries and Mike Davies in Vancouver in the early 90s, they had a similar classification, but it was very similar with these boundaries, and the boundaries were almost concentric circles. So they came up with the very clever idea that you could take an imaginary center of these concentric circles, and the radius of these concentric circles would be an index of soil behavior. So they refer to it as soil behavior type index, IC. So it's just the radius of these concentric circles. So when IC is small, you're up in the sand region, and when IC is large, you're in the clay region. And since most data plots down the middle of the chart, then IC works really quite well. And so IC is, like around 2 or less in sands, and it's usually greater than 3 in clays. And the boundary between the two is roughly 2.6. And the nice thing about the normalized charts, it's suitable for any depth. So from very shallow to very deep works really quite well. And here's the equation for IC. It's basically, it's it's the radius of the circle. Stuck on the name now. And again, color coded, very popular. And so here's the presentation in terms of normalized data. This is becoming more popular. So now you've got normalized cone resistance. And now you can see that the soft clay, instead of increasing linearly with depth, the soft clay has a pretty well constant normalized cone resistance. And of course, the normalized cone resistance is a better indicator of density. So if the normalized cone resistance in the sand layer is high, that's a denser sand than when it's lower. So you'll see later that relative density is linked to the normalized current resistance. And here's the friction ratio. Here's BQ. And so when BQ is 0, it's essentially you've got a drain penetration. And when BQ is greater than about 0.2, then you're basically into undrained. So most of the fine grain now you can see it's predominantly undrained penetration. And so you've got IC shown here. So, from 1 till 4, with 2.6 being in the middle there. And blue, of course, is clay. So when IC gets up into the blue region, it's clay. When it drops down into the brown region, it's sand. And then you get transitional data as it moves from one to the other. Now, in 2016, these charts have been around for almost 30 years. A common complaint often is that people would say, well, I like the CPT soil behavior type charts, but when I compare them with samples, they don't always agree. So why does the soil behavior type not always agree with the sample? And that's because, of course, the sample is based on a physical characteristic, where the CPT is based on a behavioral characteristic. So the CPT is saying, well, it's behaving like. It may not actually be that, but it's behaving like. And so most of the time, 90% of the time, if it's behaving like a sand, it generally is a sand. If it's behaving like a clay, it generally is a clay. But there can be cases like for example, very heavily overconsolidated clays. They tend to have a very high undrained strength, higher than the drain strength, and they tend to be very stiff, so they can look a lot like a sand. And so sometimes very stiff, heavily overconsolidated clays can begin to plot up into the silty sand region. And so it looks like it's a silty sand, but of course, if you look at the pore pressure, then often you're getting a significant excess pore pressure. And of course, if it's a very heavily overconsolidated clay, you may get a significant negative pore pressure. And then when you do a dissipation test, it'll be rather slow to come up to equilibrium. And so the fact that it's slow is indicating it's more clay-like. And so to help with that, I wanted to move away from the traditional saying characteristics of descriptions using sand, silt, and clay, and start to say, well, it's sand-like and it's clay-like. And then the intermediate stuff actually refer to it as transitional. And so the main areas is, first of all, wanted to identify whether or not the soil had any microstructure. Now, previously, microstructure was never mentioned in any of the charts, but we know when we're dealing with real natural soils, most natural soils have some microstructure. And the major issues around microstructure is aging and bonding. So the older the soil is, the more likely it has microstructure. And what I mean by microstructure is the things you can't see. So macrostructure are things like layering and fissuring, things you can see. Microstructure is what you cannot see, so at the particle level. And so aging effects, we know that soils get much stiffer with age. And of course, they get much stronger if they're bonded. And so aging tends to make the tip resistance go up relative to what the soil actually is. Now, microstructure covers the spectrum from essentially no microstructure, so a very young, recently deposited soil with no bonding would have no microstructure. And then the older it gets, you'll have increasing amounts of microstructure. And of course, if there's cementation or bonding, you'll also have increasing microstructure. And also if there's unusual mineralogy, that gives you an effect like microstructure. And so it's a spectrum. And so we drew a line and said, well, if there's little or no microstructure, it generally is behaving like a young, uncemented soil. And we know that most of the correlations work quite well in there. That's where most of the traditional data is based. And so first thing we want to do is determine, is there significant microstructure or not? And then once we've determined that there's little or no microstructure, we then want to determine, is it predominantly sand-like or clay-like? And then the next important step is we want to know, is it dilative or contractive at large strains? And we want to know that because if it's contractive at large strains, then that means it's got a tendency to contract. So if you test it undrained, you'll develop large positive pore pressures, which means the effective stress will go down, which means the undrained strength will be less than the drained strength. But if it's dilative at large strain, the dilative strength is going to be larger than the drain strength. So knowing if a soil is contractive or dilative is going to give you a sense of, should I be using undrained strength or drain strength? So if it's dilative, typically you use drain strength because that's going to be lower than the undrained strength. But if it's contractive, you typically want to check for the undrained strength because that's going to be lower than the drain strength. And then last of all, you want to know, is the soil sensitive? Is there a risk that it's strain softening? And could I get remolded strengths that are significantly smaller than the peak strength? So those are sort of the behavior classifications. And so
Excuse me,
that's what we try to do.
Dr.
Yep.
Robertson. I hate to jump in because this has been such an incredible presentation, but I do want to be mindful of the schedule, and we have so many questions piling up in the chat.
Okay.
Would you like to take one last minute to wrap up?
Okay. So I'm going to flip through it very quickly. So this was I'm going to flip through this quickly. So here's the 3 sets of charts. So the one on the end was a new one that said, okay, got normalized cone resistance on the vertical axis, and this horizontal is G0 over QT. G0 is from shear wave velocity. And what we found is that most young uncemented soils fell within a region, and if it fell outside of that region, you had microstructure. And then the chart on the left was like you've seen before, which is normalized cone resistance against friction ratio. The dashed lines are the traditional boundaries, and the solid lines were recognizing that these concentric circles weren't quite right, and we moved to hyperbola's hyperbolic shape. But you can see that I go back to here's a color coded. So, you've got sand-like material, both contractive and dilative, clay-like material, contractive and dilative, and then sensitive clay-like. And then in the middle, you've got this transitional material that could be contractive and dilative. And so you end up getting a sort of a more detailed profile, similar to that is the same profile, but now with these newer parameters. So let me just finish off and Professor Jonathan Bray once said to me, he said, so this soil behavior type chart, it's a bit like a Rosetta Stone of soil behavior. So I'm going to just quickly zip through some main things. So here's the basic soil behavior type chart. So if you know there's little or no microstructure, the chart works really quite well. So that boundary of contractive dilative works very well as long as there's little or no microstructure. And so we know, for example, that increasing unit weight tends to move up and to the right, and then decreasing permeability and increasing fines content goes down the middle and down to the left. Of course, sands have high permeability and small fines content. Clays have low permeability, high fines content. And here are the correlations that were developed that help you get that. You can estimate the unit weight, permeability, and fines content. And then if you're in the sand-like region, so if you're in this upper left region, we know that as you go up and to the right, you get increasing relative density, increasing state parameter, and increasing peak friction angle. Here's the correlations for them. They're all based on clean sand equivalent, and the clean sand equivalent is just the measured normalized cone resistance with a correction factor, and the correction factor is a function of IC. And so it's basically saying, this contractive dilative boundary. So if you've got a silty sand right in the middle of the chart, that's equivalent to a clean sand up and to the left. So that's what that clean sand equivalent correction is. And then if you're in clay-like materials, which is the bottom right-hand corner, so normally consolidated insensitive clay would plot where those two red are joining. And so increasing OCR tends to move vertically up, and increasing sensitivity moves to the left. And so depending on where the data plots on the chart, you get a pretty good idea of what the material is. So here's the relationship for OCR, undrained strength ratio, and remolded undrained strength ratio. And then microstructure, so this boundary of contractive dilative boundary, so that works for soils with little or no microstructure. With increasing microstructure, that contractive dilative boundary moves up the chart. So as you get more microstructure, that boundary begins to move up. In other words, you can have data that plots what appears to be in the dilative region, but in fact is contractive because that boundary is moving up. And one of the ways you often see that from real data is that the tip resistance might be saying, oh, this is a very stiff material, appears to have a high OCR, but the pore pressures are strongly negative. Strongly positive, which means it's contractive. So the tip is saying, it's over-consolidated and should be dilative, but the pore pressure is saying it's contractive. And so that's because of that microstructure. And you can do dissipation tests to get equilibrium and rate of dissipation. Here's just an example, pore pressure against time. You pull off the T50 value. Here it's 160 seconds, and you get the equilibrium pore pressure. And then there is a chart of taking the T50 to give you the coefficient of consolidation, and then the T50 to give you permeability. Notice that one is in minutes, one is in seconds. I've added in the range where soil is undrained or drained, so roughly 60 seconds. So if T50 is greater than 60 seconds, the penetration is essentially undrained. Here I wanted to just show an example that it's quite common that people tend to say, well, I need to know where the groundwater is. It says, yeah, you do need to know where the phreatic surface is, but you also need to know what the piezometric profile is. It's not always hydrostatic. So if there's downward flow, the piezometric profile will be less than hydrostatic. And if there's upward flow, the piezometric profile will be greater than hydrostatic. And so doing frequent dissipation tests and getting equilibrium allows you to know the groundwater conditions. So Ken talked about examples of where excavations would blow out due to high water pressure underneath the excavation. So if you do CPT and you do dissipation tests, you can anticipate you've got these high pore pressures. So to close out, key points. SPT is generally not very reliable. Avoid if possible. Ken said, for low risk projects, it's okay. Nowadays, with increasing availability of CPT, it said, look, why not just do CPT? You're going to get much better data, and it's actually going to be cheaper if it's readily available. So CPT's excellent reliability provides near continuous profiles with multiple measurements. You need to follow the standard. CPT can be carried out in essentially all the same soils that the SPT can, but you just get a lot more data. The DMT is useful, but it is a little bit more expensive and slower and gives you less data than the CPT. And so the DMT tends to be used in companion to the CPT, but on large, high-risk projects. Seismic CPT is the preferred test, but if you've got a project where you're going to do maybe 10 CPTs, you don't need to measure shear wave velocity on all 10 of them, maybe 2 or 3, just so you get the relationship for the site and basically determine whether or not there's microstructure in the soils you're dealing with. And then so you get lots of data. So for a 30-meter sounding, you get 4,500 measurements of tip, sleeve, and pore pressure. So you've got enough that you can actually run statistical analysis. So you know what the mean and standard deviation of the parameters are. And then, of course, if you do dissipation tests, you may get an additional 150 additional measurements of U0, T0, and shear wave velocity. So no other in situ test provides that amount of data in a cost-effective manner. Now, I know I went by quickly, but you do have the slides available on the server to download and look at it in your leisure. And as they said in the introduction, I've had this CPT guide around for about 20 years, so it's on the 7th edition now. It's free at a number of different websites, and also I've got webinars that are freely available. And then Professor Paul Main, in collaboration with Contech, they have a similar manual. Paul's is a little bit different. He's focusing more on parameters, but the two together are very valuable. Mine tends to be shorter and more concise. Paul is more detailed, but Paul has a lot of good examples in there, so both are very, very useful. So sorry if I rushed it a little bit near the end, but happy to take any questions.
Thank you so much, Dr. Robertson. That was a fantastic presentation. Great to see the background behind the science of these charts and how we can predict some behaviors, some parameters of the soil. So leading up to questions, we have one here just on one of your last points about dissipation, and it's about application and tailings. To what extent are dissipation tests reliable in tailings, particularly when partial saturation leads to non-monotonic dissipation curves and atypical pore pressure responses that are difficult to interpret?
Yeah, that question touches on a couple of things because you say a partial saturation. So first of all, ideally, of course, the cone needs to be saturated. And, 50 years worth of experience, contractors are getting much better at saturating their cones. And usually they use a viscous liquid like glycerin or silicon oil, which has a higher viscosity, and they use porous stones that have a relatively small pore space, so they can maintain saturation for a long time when pushing through partially saturated materials. So saturation is less of a problem than it used to be. Now, when I threw in that one slide that talked about non-hydrostatic piezometric profiles, that of course is very common in tailings. So particularly tailings near the dam, where the phreatic surface is going to be diving down as it approaches the dam. So you've got flow downwards and towards the toe of the embankment. So you've got downward flow. And so it's common that groundwater conditions are not hydrostatic. And this is a common problem in tailings, is that people do dissipation tests and they start to question the dissipation tests and say, well, I'm not quite sure why it's giving me these numbers, why it's so low, where we know that the water table is quite high, so why am I getting such low numbers? And of course, a lot of it, we've got strong downward flow. And that's important, because if you're going to install piezometers, if you put one piezometer in, you will not get the correct phreatic surface, because if there's downward flow and you're assuming hydrostatic from that piezometer, you're not going to get the correct groundwater surface. And so you need a minimum of 2 piezometers in a vertical profile to get the correct groundwater. So generally, I find dissipation tests are very good in tailings. Tailings tend to be highly interbedded, so the T50 value can vary significantly. So if you've got interbedded tailings of coarse and fine tailings, so sands and silts interbedding. So if you stop and do a dissipation, it can be influenced by the layering above and below. So it's obviously not in a homogeneous environment. So you might be stopping in a silt layer, but immediately above is a sand layer and a sand layer below. So the dissipation is not truly one-dimensional. So it's three-dimensional as it dissipates to the adjacent layers. And so that does complicate the interpretation somewhat. But again, if you do lots of dissipations, you begin to get a sense of it. And so, for example, in South Africa, it's very common that they'll do dissipation tests every rod change. Now, the rods are 1 meter long, so it's common that they'll do a dissipation test every meter. And because the tailings are predominantly sandy and silty, dissipations are very rapid. So it takes usually less than a minute for dissipation. So they'll do lots of dissipations, and they'll get a detailed profile of the piezometric profile, which is really valuable. Now, if it was an ideal world, you do one sounding that says, well, why don't I do one sounding where I don't do any pauses? I'll just do a continuous sounding, and then I'll move over and do one where I do very frequent dissipation. So if the budget allows it, that can be an optimum way around it, doing a mixture between the two. Often what happens is, if you've got a large project and you may be doing 20 or 30 CPTs, it says, well, you want to do a minimum of 2 or 3 dissipations per sounding, but you don't have to do them every meter or every 2 meters. But in some, it's worth doing more than others so that you get a real sense of what the piezometric profile is. So dissipation tests are very useful. The interpretation can be complicated because ground conditions are not ideal. They're layered, and so theory doesn't always apply exactly. But usually the equilibrium is insightful and the rate of dissipation is insightful. But you got to remember that permeability varies by orders of magnitude, and so T50 will vary by orders of magnitude from sort of 1 to 10 to 100 to 1,000 seconds. And so it's that order of magnitude you're looking at.
Thank you very much, Dr. Robertson. This is so insightful. We appreciate you, appreciate everyone that participated. This is all the time we have for questions today, and I'll pass it over to Chelsea to close.
Hey, yes, thank you again, Dr. Robertson and Ken Scaffield, for kicking off our short course series. Just want to give a big round of applause again, virtually to all your work. Thank you.
You're welcome.
Yeah. Just a reminder, the recording will be available for all the sessions to each of the registrants. And then will be available also on the CGS database if you're a member. So thank you again, and we'll see you next Wednesday.